To start our next presentation. Thank you all for coming. I'd like to introduce Shawn Smith. I've had the pleasure of having Shawn in class 4 times now, 4 different classes, of course. But he's had the opportunity to, I think, marry 2 things. I dare say he loves hunting and mechanical design. So take it away, Shawn.
Thank you. As Dr. Smith said, my name is Shawn Smith. Today I'll be presenting to you my senior design project concerning the engineering of a rotating hunting stand. My advisor is Dr. Natasha Smith, and my major is engineering with a mechanical emphasis. Before I begin, I'd like to thank a few people. First and foremost, I'd like to thank God. Without God, none of this would be possible. Secondly, I'd like to thank my parents, Dave and Jolene Young, whose care and support has helped me get to this level. My grandparents, in particular, Linda Goodwin, whose support and constant prayers have helped me to get where I am. On a professional level, I'd like to thank the University of Southern Indiana, whose graciousness, as far as the campus goes, the students, the faculty, has been overwhelming. I would like to thank Dr. Natasha Smith, my advisor, whose constant work and dedication has helped me to create a better project. I'd like to thank Dr. Julian Davis, who has donated his efforts and material to help this project. If you don't mind, I'm going to take a break because I'm freaking out up here. Can I take a minute break and step outside?
Take a deep breath. Don't need to be nervous.
You guys will have to forgive me. Public speaking is not my favorite thing to do. I'll start over. My name's Shawn Smith. I'll be presenting to you today my senior design project concerning the engineering of a rotating hunting stand. My advisor is Dr. Natasha Smith. Before I begin, I'd like to thank a few people, in particular God, who has helped me get to the point where I am, my parents, Dave and Jolene Young, whose care and support has helped me to achieve this level of success, my grandparents, in particular, Linda Goodwin, whose care and support has helped me reach the pinnacle where I am. I'd like to thank the University of Southern Indiana. In particular, I'd like to thank Dr. Natasha Smith, my advisor, who graciously donated her time and efforts even though she was overworked to help me create the best project that I could. I'd like to thank Dr. Julian Davis, who volunteered his time and materials to help me create this project. I'd like to thank Dr. Zane Mitchell, who spearheads the engineering department, and Donna Moore, who keeps the engineering department running smoothly. So the purpose of this report is to create an innovative rotational hunting stand to satisfy the requirements from a senior design project. Throughout this report, I'll review the objective of the report, background concerning the report, the problem, designs to solve the problem, analysis of those designs, a budget and risk of the design, and a conclusion. So the objective is to create a hunting stand that can rotate around a tree, thus creating a larger field of view. This increases the hunter's odds of being in the right position when the deer comes. What inspired me to create this report was I have extensive experience with machine design and fabrication through Toyota Bashuku of America and Hearst Manufacturing. Additionally, my time here at USI has been primarily dealing with machine design. I'm also an avid hunter, and I've been hunting since the age of 11. So some background. Each year, nearly 10 million individuals participate in deer hunting. These hunters spend approximately $10.7 billion on hunting-related gear. Arguably, the most crucial piece of hunting-related equipment is the hunting stand, as it positions the hunter up in the tree, away from the deer's line of sight, thus concealing them. So the reason that they do that is deer are cunning creatures. They're always alert, and they have unique behavior that varies based upon temperature and barometric pressure, seasonal changes, and all kinds of other variables. Deer stands give hunters an advantage over the deer. One drawback with the current design of most deer stands is that they're stationary. These here are just a few of the deer stands that hunters tend to use. The most popular is probably the homemade hunting stand. Homemade hunting stands, as you can see, are just assembled from parts that are lying around. In this case, a couple pallets and an old pickup. States are now prohibiting these type of deer stands. They are recommending that you use TMA approved designs, which is the Tree Stand Manufacturers Association. So my solution is to create a safe, reliable tree stand that can be rotated around a tree, thus giving a better field of view and greater versatility. These here are just some traditional hunting stands: the buddy stand, the climber stand, the platform stand, and the platform blind. And each of these types, they're very popular, but they're also stationary, so they limit the hunter's view. My design would enable a 360-degree view. So, literature review. A few rotating hunting stands have been attempted, but they've all tended to miss the mark. These are just a couple examples here. The Revolution faces the hunter inward towards the tree, so it's kind of like you're constantly playing a game of peekaboo with the deer. The Johnson 360 tree stand has a swiveling seat, and so the seat can swivel 360 degrees, but at the same time, supporting tree and other foliage is still blocking the hunter's view. So my game plan in order to create this rotational hunting stand is first to identify the hunter's needs, which from this I will gather the hunting stand requirements. Then I will create the design concepts. I will evaluate those designs and select one, and then I will build and test the designs. So a hunter's needs. A hunting stand should be safe, easy to access, provide a greater field of view, economical, quiet, comfortable, and versatile. Based upon this, I established that the hunting stand should weigh no more than 175 pounds in weight, should be capable of resisting a 350-pound load, so a guy like me can actually use it. And it should not have a deflection of more than ½ an inch, should be capable of 270 degrees of rotation. It should be mountable to an average tree, which I deem to be 24 inches in diameter. The actual recommended tree size for deer stands is 12 inches or greater, but to be on the safe side, I said 24 inches. The whole design shall be constructed to have a design factor of safety of 1.5. And then the project itself should be completed by December 10th with a budget of under $400, which I deem to be a realistic amount for a student. So my designs. The first design, which I deem the circular railing system, consists of a I-beam, which a seat platform will ride along kind of like a monorail. And the seat will be able to rotate around the tree 360 degrees. It'll have adjustable support members to match the tree's diameter. It will come equipped with a guardrail system and a standing platform as well. Design B, which I deem the swing arm system, consists of a support arm which will be attached to the tree, a swing arm which will be pinned to the support arm via a pin connection, and then a seat with a standing platform and a railing system which is attached to the end of the swing arm. I then evaluated each of these two designs based upon four criteria: safety and comfort, cost and schedule, feasibility of the design, and the mobility and motion. Since both designs have been attempted before, but never actually fully achieved, I said that the safety and comfort could technically be achieved for both. The cost and schedule, I believe that the swing arm would be easier to do since I have experience with cantilevers. The feasibility of the design, once again, because I have experience with cantilevers, and because most hunters would view the swing arm design as a typical hunting stand design as far as the appearance, I gave it the edge on feasibility. And the mobility and motion, I deemed that the circular railing system would be easier to operate for the hunter. Based upon this analysis, I selected the swing arm design to be implemented. I then created a systems analysis. As you can see here, I broke down the rotating hunting stand into 3 separate systems: supports and frames, the hunting stand, and the rotational mechanism, which will be used to move the hunting stand. This is my solid model design. As you can see here, I've got a support arm that measures 48 inches long. It's a 5x5 square area, and it's 0.125 inches thick. The swing arm is 36 inches long, and it measures 3x5, and it is also 0.125 inches thick. Most of the assembly will be constructed from T6 6061 aluminum alloy. The pin itself, however, because it's much smaller, would need to be created from something with a much stronger. So I selected 1215 carbon steel. SolidWorks calculated the weight to be 188.62 pounds using these materials, which is approximately 7.5% from the target goal of 175 pounds. I have here the mounting system, which will be used to attach the device to the tree itself. As you can see, the top mounting bracket has 6 bolts, the lower mounting bracket has 4 bolts, and the top mounting bracket is equipped with 2 locations for ratchet straps, which are the typical mounting devices used with hunting stands. Here's a diagram of the seat motion. The seat will be able to swivel 180 degrees using a ball bearing. You'll have a lever that you'll have below you. You'll pull the lever, it'll release a pin from this circular plate that has holes pre-drilled at 15-degree angles. And it's also collapsible for easy transport and assembly. And then the rotational mechanism. The rotational mechanism will consist of a worm gear with a worm, a rotating spur gear, and a stationary spur gear. I deemed that the hunter would rotate the handle at 1 revolution per second. This will produce 1/60th of the rotational velocity. So as far as my design analysis, I analyzed my design in 2 separate ways, through hand calculations and SolidWorks models. For SolidWorks, I'll analyze the stress, the factor of safety, and the deflection. For the hand calculations, I'll analyze the stress, the factor of safety, and then the bolts analysis. So my meshing constraints for the SolidWorks model, I fixed all of the bolt hole locations, and then I applied a 350-pound downward vertical load at the end of the swing arm. As you can see here, I checked each of my 3 separate angles, which I deemed to be 90 degrees, 45 degrees, and 0 and 180 degrees. I checked all of those for mesh convergence. My stress analysis. So my stress analysis, my maximum stress turned out to be 27,986.9 PSI. And then in the 3 separate angles, for the 0 and 180, my maximum stress occurred at the pin, whereas for 45 and 90, it occurred at the lower mounting bracket. This stress value for the 90 degree angle, which is also the angle that I used to do the hand calculations, differed by almost 93.22%. This is a big difference. So basically what that says is that my hand calculations were too generalized. I then performed my factor of safety. This is a few images of the factor of safety of using a von Mises failure surface. As you can see here, the red areas indicate areas that are at or near the minimum factor of safety, which in this case, the minimum factor of safety turned out to be 1.43. I then compared all of the factor of safety calculations to my hand calculations for SolidWorks. I then analyzed my deflection. As you can see here, the greatest amount of deflection occurs at the 45 degree angle. and it is 0.547 inches, which is 8.98% greater than the deflection limit of 0.5 inches. I then analyzed the bolts using hand calculations. I used a quarter 12-15 steel bolt measuring 3 inches long with a 1/4 USS flat washer. It would be used to mount the aluminum bracket to the hardwood tree. The hardwood tree would then have the bark scraped off so it would be safer. I used 6 bolts for the top, 4 bolts for the bottom, and I analyzed this and found that the factor of safety for yield was 1.17 for the bottom and 1.26 for the top. So after I found that my design was feasible, I began to create my prototype. The prototype was constructed to approximately 3/4 scale. It was made out of pine wood, mainly because it was cheap and easy to acquire and easy to work with. The prototype, as you can see here, it works as far as the swiveling, but the rotational mechanism doesn't work. The main reason for this is that the pieces that were used to create the rotational mechanism were plastic, that and the tolerances that were done to create this. I'm not a master woodworker, so we'll put it that way. But if I was going to make this out of metal, I'd actually be able to have it machined, and it would probably work. Future prototypes will have to be created to ensure that. This right here is my prototype budget. As you can see here, I have a total of $112.39. And then this is my estimated budget for the completed design. It comes to be $435.79. This is slightly over the $400 limit. With labor and advising included, the total would be just over $3,000. I then performed a failure modes and effects analysis of the design. As you can see here, I have several components, their failure modes, results of the failure, and steps that I've taken to ensure that the failure doesn't occur. So as far as future considerations, like I said earlier, future prototypes will have to be constructed to ensure that the design is capable of working, in particular the rotational mechanism. Additional designs will be tested, including geometry such as round bar versus square tubing, and I will also attempt to prototype a circular railing system. I'll evaluate the design using ratchet straps rather than bolts, or a combination of ratchet straps with teeth. And then I'll also examine removing the extended cantilever beam to reduce the deflection, weight, and cost. The portion of that I'm actually talking about is this portion here that extends past the support brace. Once I've created a completed design, patents will be filed, and then a marketing strategy will be created. I actually came up with a name and a slogan, Pivotal, giving hunters the pivotal advantage. I made that in paint, I'm pretty happy with that. But as far as my clients go, I want to pursue extreme hunters, people who spend a lot of money, they have extreme passion for the sport. This includes hunting ranches or just shows that have hunters on them. Conclusion. So based upon my analysis, the design is feasible. As you can see here, the stress was below the yielding limit for aluminum. The safety factor needs a little bit of work. It's 1.43, whereas my required safety factor was 1.5. The deflection was also pretty close to what I intended to achieve, 0.547, where the requirement was 0.5 inches. And then the weight was slightly over the 175-pound limit as well. The prototype shows that the structural design is achievable, but the rotational mechanism needs work. Future prototypes will be tested and completed design will be proposed to hunting equipment companies. These here are my references, and way too many. And thank you for your time. I greatly appreciate your feedback.
Yes. A comment and a question. One of your slides you alluded to waiting for your prototype to be complete before you file for a patent. If you're serious about filing for a patent, you don't need a working prototype. Your drawings are fine. Sooner than that. My question is in regard to your lag bolts that you're screwing into the tree. Is there any part of that analysis that considers the type of wood that you're screwing those bolts into, whether it's an oak tree or a pine tree, and how does that affect, the final design, what bolts should be used, et cetera?
That's a good point. The type of wood that I used for the tree in that analysis was red oak, just because I thought that was something that was pretty popular out there, and it seemed to be a pretty good mid-level range for as far as trees. That's something that I'll actually have to look more into when I start to develop the completed design.
The one question I had, and looking forward, is how is somebody going to get on to the seat? And the reason I'm asking that is not from a practical standpoint of getting on it, but is that going to create torsion, and is that a problem?
Yeah, that's something I'll probably have to examine as well. Ladder placement can really be crucial in these type of designs. I'm flirting with the idea of having a spring that will bring the swing arm back to a default position, and then using a ladder on the tree. But like you said, that'll also create torsion. And then I'm also contemplating just sticking a ladder in the front, but I'll have to examine the torsional effects on the seat as well.